Hello children, today we will be doing the part of extraction of aluminium. The topics covered will be under extraction of aluminium, it will be chemical method for purifying bauxite by using sodium hydroxide. This is known as Bayes process, as well as electrolytic extraction, which is known as Hall-Herold's process. In both the cases, we have to go through the structure of the electrolytic cell, their various components as part of the electrolyte, then electrodes, electrode reaction, etc. So the chemical, first we will be discussing the Bayes method. You know aluminium symbol is Al. Its relative atomic mass is 27, atomic number is 13, valency is 3. It's generally a silvery white metal, specific gravity is 2.2. You know the electronic configuration is 283, its position in periodic table is period 3, group 13 or old group 3A. This is the most abundant metal in the Earth's crust, very reactive metal, so it doesn't available in the free form in the nature. It was first discovered in Orsted in 1825. Hall and Herold in 1885 developed the process for extraction of aluminium, which also we will be going through. Aluminium is generally extracted from its main ore, that is bauxite. Its formula is Al2O3.2H2O. Now bauxite contains 60% of Al2O3 and rest is sand, ferric oxide and titanium oxide. It is generally concentrated or purified by the chemical method. So we go through the purification process, which is called Bayes process, which is the conversion of bauxite to alumina. Now you first see the bauxite is grinded finely and then heated to remove the volatile impurities. Then it is heated under pressure with concentrated caustic soda solution for 2 to 8 hours at around 140 to 150 degrees Celsius temperature, and this process is called leaching. So the reaction is Al2O3.2H2O plus NaOH. It will be 2 NaOH, we will be getting 2 NaAlO2 plus 3H2O. So now here bauxite dissolves and it forms sodium meta-aluminate. So this is sodium meta-aluminate, NaAlO2. Because of the atmospheric nature, because of the amphoteric nature, sodium, you know that aluminium, zinc, lead, tin, these are amphoteric in nature. So because of the amphoteric in nature of aluminium, it forms sodium meta-aluminate. So it leaves behind the insoluble impurities which is called red mud, and red mud contains ferric oxide, sand, etc., which are removed by filtration. Now you go dilute the sodium meta-aluminate with water and then cool to 50 degrees Celsius. It will be hydrolyzed to give aluminium hydroxide, which will be there as a precipitate. Other soluble impurities will be dissolved in sodium hydroxide. So here the reaction is NaAlO2 plus 2H2O gives you aluminium hydroxide precipitate and sodium hydroxide. Now this precipitate is filtered, then washed, dried and ignited at 1000 degrees Celsius to get alumina, which is Al2O3. The reaction is shown over here. The filtrate containing sodium hydroxide is again used to extract the aluminium from the bauxite. So this sodium hydroxide solution can be reused. Now aluminium oxide is present in the nature due to its great affinity for oxygen. So it forms a very stable compound. Now it is not easily reduced by common reducing agents which we had discussed in previous videos, carbon, carbon monoxide or hydrogen. So the electrolytic reduction is chosen as the method for reducing alumina. By this time you might have gone through this question, why electrolytic reduction is chosen for reducing alumina. So this is the answer. So what difficulty generally is faced for obtaining aluminium from alumina? Electrolytic reduction is done generally in molten state. Now alumina melts around 2050 degrees Celsius, but at this temperature whatever aluminium is obtained, those are vaporized. So it is not very easy to collect. So now this difficulty was removed by Hall. He found a suitable solvent in another ore of aluminium, which is cryolite. Cryolite is Na3Al(F)6. Now when he applied the current to the molten mixture of alumina is Al2O3, then which is 20%, cryolite, that is 60%, cryolite formula is Na3Al(F)6, and calcium fluoride 20%, that is CaF2. He saw some shining globules of aluminium appeared at the cathode. So he was very happy over this success of his 3 years efforts, and then immediately ran excitedly to his professor and presented to him a very small pieces of the metal. This happened in 1886. Now Hall's discovery revolutionized aluminium industry. Aluminium, which was once a costlier and rarer metal than gold, became a cheap metal of common use in every household. Now come to the electrolytic extraction, which is Holt-Hero's process. Electrolytic reduction of fused aluminium. Here you have one electrolytic cell. You can see the cell over here on the left side. It is a rectangular iron tank with a sloping bottom. This is the sloping bottom. There is a tap attached over here. This tank is the tank is lined with the gas turbine, and the sloping bottom is facilitating the tank to remove the molten aluminium through this tap. Now the electrolyte is the mixture of molten alumina, as we have discussed just now. Then cryolite 60%, molten alumina 20%, cryolite 60%, and fluorspar or calcium fluoride 20%. Powdered coke is sprinkled over the electrolyte surface, and the temperature of the molten electrolyte is maintained at around 950 degrees Celsius by electrical heating, and the voltage is kept around 5 to 6 volt because low voltage is used to avoid the decomposition of molten cryolite. So these are all precautions you have to remember. Now the reactions you get for the cryolite Na3Al(F)6, you get 3Na plus Al3 plus 6F minus, and then CF2 plus fluorspar CaF2, you get Ca2 plus 2F minus. Then alumina 2Al3 plus and 2O2 minus, 3O2 minus, sorry, it will be 3O2 minus. Now positive ions are formed. Positive ions are formed. Who are the positive ions? Sodium, calcium, aluminium. And the negative ion forms are fluoride and oxygen. Now aluminium is lower in the electrochemical series, so there will be the preferential discharge at cathode. Similarly for the oxygen at the anode. Now cathode is the inner carbon lining of the electrolytic cell, which we have said already. The cathode is the inner lining, which is gas carbon, and these are the anode, graphite. Now here the reaction is taken place, 4Al3 plus 12V, you get the 4Al, and the thick rods of graphite which are suspended into the fused electrolyte, these are the anode. 6O2 minus 12V, you get 6 oxygen, and then you are getting 3 molecules of oxygen. Now here what is happening, due to the deposition of oxygen, the anode is getting oxidized, first to carbon monoxide and then to carbon dioxide. So you have to replace the anode time to time as it gets oxidized by the oxygen which is evolved at the anode. Now some more precautions you have to take. As the supply of alumina decreases, the voltage rises up to 40 to 60 volts. We have discussed that voltage should be maintained at 5 to 6 volts. So it increases to 40 to 60 volts as alumina gets reacted. So you have to add the fresh alumina. And now how do you know how the voltage is rising? If you add some bulb in the series with the apparatus, it will glow very brightly. So you have to add the fresh alumina. Now aluminium obtained by this method is 99.8% pure, and further purification can be done by the electrolysis. Now use of cryolite, it lowers the diffusion temperature from 2050 degrees Celsius, it's not 2050 degrees Celsius to 950 degrees Celsius and enhances the conductivity. So you have to use the cryolite because it reduces the fusion temperature from 2050 to 950. Fluorspar and cryolite are used as a solvent for electrolytic mixture, which increases the conductivity as alumina is almost a non-conductor of electricity. And powder coke is used to reduce the heat loss by radiation and prevents the burning of anode. This is the flow chart of extraction of alumina. At a glance you can have the whole process. First one is the Bayes process and then Hall-Héroult process. The refining of aluminium is not there in your syllabus. Thank you so much. Thank you for patience hearing.